Okay, so first of all, we have Sheldon to explain to you what the Doppler effect is, if we have volume.
Ongoing is the Doppler effect. No, it's not. If I have to, I can demonstrate. Meow. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's right. Peter Pan! I got a handful of pixie dust with your name on it.
No, you don't. I hate what Sheldon's supposed to be.
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay. See? People get it.
The key bit, other than Sheldon imitating the Doppler effect, was his definition of it. Okay, so his definition is this down here. Okay, the apparent change in frequency caused by the relative motion between the source and the observer. Okay, so the sort of key bit is it's the apparent change. The actual frequency that is being emitted by our source, by our ambulance or whatever we've got, okay, is not changing. But because there is motion, okay, between the source and the observer, the frequency appears to change. So what you would hear if you were standing behind or in front of would be different to the actual frequency which the drivers would be hearing. Okay, so if we look at our diagram for a minute, and we'll watch that video and they'll explain it again for you. Okay, if we look at the left-hand side of that diagram first of all, we are standing so that our source of sound or source of light, whatever it is moving away from us. Okay, and because they're moving away from us, the waves or the wavelengths appear to be stretched. Okay, because that source of sound or source of waves is moving. Okay, so because our wavelengths have increased, they've got longer, that means our frequency, remember the number of times something happens per second, has got lower. So if you are behind the source, okay, and the source is moving away from you, we have a lower frequency, a longer wavelength. So if we're looking at sound, we have a lower pitch. Okay, it's going to sound lower than actually what it is. Okay. If we look at the right-hand side, okay, we're now in front of the source and it is moving towards us. Okay, so because it is moving towards us, the wavefronts will bunch up together. Okay, our wavelength appears to be shorter, so the frequency appears to be higher. Okay, so we're expecting a higher pitch if we're talking about sound. Okay, so we can hear the true frequency. Okay, but you have to be directly at right angles, perpendicular to the source. Okay, and at that point you will hear the true frequency. Okay, so the key bit is having relative motion between the source and the observer, right? If we're thinking about the people inside the vehicle, okay, for them it sounds the same all the time, okay, because they are moving with the source. There is no relative motion, okay. They're moving with the source, and so for them, the wavelengths are not bunching up or they're not spreading out. They're not doing any of that stuff. Okay, and so they will be hearing the true frequency all the time. Okay, it's only for us sort of outside of that system that we're hearing something different.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look at your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its colour. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change colour depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence of the Big Bang and an indication that the Earth might get very lonely in the distant future.
Hopefully that showed you what's happening in terms of both sound and light. Okay, so yes, technically, if one of you walks to me, your blazer is going to change colour slightly. Okay, but the human eye is not sensitive enough to detect that change. Okay, so if you are moving towards me and I am standing still, okay, what we have is we have white light from our lights or from the sun that is going into your blazer. Your blazer is absorbing every wavelength except that lovely teal colour. Okay, which is getting reflected back to me. Okay, so you can only see things where the light is being reflected and enters your eye. Yeah, so if you walk towards me, okay, the light that is being reflected off your blazer, that tealy blue shade, okay, the frequency of that is going to increase slightly as you walk towards me because those wavefronts are going to bunch up a little bit. Okay, but we are not sensitive enough to detect that slight change, okay, as a human, okay, but it will be happening. So, we have an equation. This is down the bottom here, okay, and we've got a few variables and we've got some subscripts that we need to just be really careful of. So, apparent frequency is our f dash. That is what we are appearing to here, depending on where we are in relation to the motion. Okay, so this f apostrophe thingy here. Okay, the next bit is we have two different velocities. So we have v with the subscript of w for the velocity of the wave. Okay, so if we were to look at just a stationary source, okay, without it moving, without us moving, we would just have the velocity of the wave. How fast is that wave traveling, right? So if we're talking about sound, it's usually around 340 in air. If we were talking about light, it's our 3 times 10 to the 8 meters per second. So those would be our velocities of the wave. The other velocity we have is v with the subscript of s, velocity of the source. So how fast is our ambulance or our star or our plane or whatever it is, how fast is that going? And then the final bit is f with the subscript of s. So what is the true frequency? What is the frequency at the source? Okay, what is our ambulance driver actually going to hear? Here is our base, v equals f times lambda, our wavelength, and we do some rearranging and we end up here. Now, in your equation, you have that plus minus symbol that you saw when we were looking at uncertainties. You're not going to use it like the plus minus with our uncertainties. What we're going to do is you have to pick either the plus or the minus depending on the scenario. If we are behind the object, if the object is moving away from us, okay, we're hearing a longer wavelength, we've got a lower frequency, we've got a lower pitch. Okay, in that case, you are going to add your wave velocity to the source velocity. Okay, so they're both up here if you need a sort of deconstructed version of it. Okay, so if the source is receding, it's moving away from you, you're going to add those two velocities together, the velocity of the wave and the velocity of the source together. If we are now in front, so on this right hand side of this diagram, if we're now in front of the source and it is moving towards us, that wavelength is going to appear shorter. We have a higher frequency therefore, so we have a higher pitch or a different colour. In this instance, okay, you are going to minus the source velocity from the wave velocity. So if it's coming toward, it's going away from you, you're going to add. If it's coming towards you, you are going to minus. Okay, but you just get one equation on your formula sheet and you need to work out which way it's going. So if it's going away from you, you are adding. If it's coming towards you, you are minusing. Okay? And for maths people, what that does is it's changing your denominator for this fraction in the brackets here, right? So if we have a larger denominator, right, if we have 1 at the top and we have a larger denominator, what is that meaning in terms of the size of the number? If we turn that into a decimal. If we have half versus a quarter, half is bigger. Okay, so 0.5 versus 0.25. Okay, so as we increase the denominator, our decimal version of that becomes smaller and smaller and smaller. So what you're doing is you're timesing your actual frequency by a smaller number. Okay, and so your frequency, your observed frequency, will reduce. Okay. On the other end, if it's coming towards us and we make our denominator smaller, so we go from a quarter to a half in terms of the value, okay, we're actually making the number in this in these brackets, that fraction, we're making it bigger. Okay, so we are going to have a bigger number, or we're timesing our actual frequency by a larger number, so therefore getting a higher frequency that is being observed by us. Okay, so if that way of thinking about it works for your brain, go for that way. Okay, otherwise, if it's moving away from you, you are adding. If it's coming towards you, you are minusing. Okay, so we hear it most with sound, right, in terms of ambulances and cars driving past, all of that kind of stuff. That we've done before. Okay, we also have it anywhere we have waves, okay, and some common ways for us to use that are looking at speed guns and speed radars. Okay, they use the Doppler effect to work out whether you are going too fast. Okay, they talked about the redshift in that video before. So that's our diagram there in terms of if things are moving towards us, they go sort of bluey, more bluey purpley than they actually are. And if they're moving away from us, they go slightly more red. Okay, and the reason we're calling it redshift, not blue or purple or violet shift, okay, is because most of the things that we have measured in our observable universe are moving away from us. Okay, so the redshift, okay, this left-hand side, is significantly more common than that right-hand side, than the blue shift, than stars and other objects coming towards us. Okay. So, a sonic boom then. So far we've talked about, yes, the car is, or the object is moving. It's moving probably at a bit of a steady pace, but the waves are still moving faster than our object. Okay, what happens with a sonic boom? Yeah, so that's that bottom picture with the plane. Okay, this is condensation that forms around the plane. That's what that visual bit is. Okay, so a sonic boom is where basically you are going faster than the waves you are emitting. So in this case, the plane is going faster than the sound waves it is emitting. And what that means is all of your waves in front of you, basically those wavefronts end up on top of each other. So you end up with like a wall of sound. Okay, those waves are happening all on top of one another. So instead of sort of this radius of waves that you've emitted, they are all on top of each other. It's all one line. Okay, and what you do when you break the sound barrier is you physically go through this like wall of sound that you have created by going faster or at the speed of sound. Okay, and when you break that barrier, you are going faster and you hear this boom. Okay, so what happens when we watch these, and we'll watch one perhaps in a minute, is you will see the kind of condensation building up. So basically you're making a little mini cloud around the plane. Okay, and then there's kind of like almost a crack, a bit of a bang that happens when they have gone through all of those waves that have been built up.